Hey, welcome back to my channel. In this video we are going to learn what happens if we carry out a reaction on an aromatic ring that already has a substituent or two substituents. Let's focus first on the case with one substituent. If an aromatic ring has a substituent, this substituent is going to affect the reactivity, making it more reactive than benzene, in other words, activating it, or making it less reactive than benzene, in other words, deactivating it. The second thing that is going to happen is the effect on the orientation of the reaction. Here I mean dictating the position of the aromatic ring, ortho, meta or para position for the second substituent. Let's take a look at those examples on iPad. As you can see in this first case, as a reference is benzene. So if it has one substituent as nitro group, is going to be 10 to minus 8 less reactive than benzene, so deactivate the ring, a nitro group. The reason I will explain in a moment. For the hydroxy group here, it activates the ring, making it 1000 times more reactive than benzene. The X, let's consider this as a first substituent, it is going to dictate also the position of the second substituent, ortho, meta or para position. Okay, but I will talk for this again. I will come to this again. Keep in mind that substituents are classified in three groups: ortho and para directing activators, ortho and para directing deactivators, and meta directing deactivators. Let's take a look at a scheme on iPad. Let's take a look at this scheme. Benzene is here as a reference. As you can see here, methyl, methoxy, NHO2, OH, amine group, phenyl group, all of them are ortho and para directing activators. As for halogens, they are ortho and para directing deactivators. I will explain that. As for N-nitro group, sulfonic group, carboxylic group, aldehyde group, cyanide group, carbonyl group, ester group, all those are meta directing deactivators. Okay? As you can see, reactivity increases from left to right. Okay, you can feel free to make a screenshot of this scheme. It's helpful to predict the position on the aromatic ring of the second substituent. But what are the reasons behind this behavior? Explanation in detail is a long story, but the shortest answer is related with electron donation and electron withdrawal property of this substituent. If you watched my previous video on organic chemistry playlist, you may remember that the intermediate species in electrophilic substitution reaction to the aromatic compounds was a carbocation, so the electron donating groups makes the carbocation more stable, consequently making the aromatic ring more reactive toward electrophilic substitution, in other words, activating it. On the other hand, electron withdrawing groups make the reverse process, so withdrawing electrons from the aromatic ring, making the carbocation intermediate less stable, so the ring is less reactive or deactivated. As you can see here, if you have a substituent that withdraw electrons from the aromatic ring, it is going to deactivate the ring. And if you have a group, a substituent that is going to donate electron, is going to stabilize the carbocation intermediate in electrophilic substitution, so activating the ring. But what makes a substituent donate or withdraw electrons? There are two effects that are involved in this game: the inductive effect and the resonance effect. Let's start with the first one. Inductive effect is related with electron donation or withdrawal through sigma bonds due to the difference in electronegativity of the substituent and the carbon at the aromatic ring. Let's take a look at one example. As you can see here, chlorine is more electronegative than carbon here, so it creates a delta negative. So deactivate the ring. Hydroxy group also has an inductive effect that deactivate the ring. Carbonyl groups also has an inductive effect that deactivate the ring. Methyl group has an inductive effect that activates the ring. Okay, the opposite. All this is related with electronegativity difference, okay? Keep in mind this. Now let's move to the resonance effect. It is related with the donation or withdrawal of electrons through p bonds due to the overlapping of the p orbitals of the substituent with the p orbitals of the aromatic ring. How does this translate? Substituents that has double bonds or triple bonds contain p bonds are involved in the resonance structures. But also substituents that contain lone pairs are involved in the resonance structures. Let's take a look at this example. Okay, let's take a look at the resonance effect. On the electron withdrawing groups, such as a carbonyl group, is going to withdraw electrons from the ring. So this pi bond moves here and this bond moves here, so destabilizing, so deactivating the ring. In the case of chlorine, it moves one pair of electrons here by creating a double bond here, and here remains a negatively charged anion, so activate the ring. Also in the case of the hydroxy group, it donates electrons and again activate the ring. So electron donating groups activate the ring, electron withdrawing groups deactivate the ring. Let's take a look now at this table. As you can see here, this is a summary of all common groups, all common substituents that are substituted to the aromatic ring. Let's take a look at this table. As you can see, methyl group OH and NH2 activate the ring and they orient toward ortho and para position. Halogens deactivate the ring, but they still orient in ortho and para position. The activation comes from strong withdrawal through inductive effect. And deactivating groups are those ones that you see here, nitro, cyano, carbonyl groups, and they orient in meta position. You can also feel free to make a screenshot of this table. Another thing worth mentioning is why some groups direct on ortho and para position and some others in meta position. Inductive and resonance have also effect on the orientation of the electrophilic aromatic substitution. Let's move to iPad to take a closer look through examples. Let's see, here are a lot of resonance structures. Don't worry, no need to memorize them. But just to explain why, for example, phenyl orients in ortho and para position. First reason is it has more resonance structures compared to meta position. It has 1, 2, 3, 4, 1, 2, 3, 4. First reason for orienting in ortho and para. But another reason is that it has more stable compounds in ortho and para position due to the stabilization of the carbocation intermediate due to the donation of the electrons from the OH. As you can see here, donation and stabilize this carbocation here. Again, in para position, it stabilized the carbocation that was the intermediate species on electrophilic substitution. Let's move now to chlorine. Chlorine is another example. Again, the reason is the same. More resonance structures, more stabilization of the carbocation intermediate. As you can see here, it's stabilized, more stable, the most stable compound, and here again stabilize here and is the most stable compound. Okay, let's move now to the case for a carbonyl compound that is typically for orienting in meta position. As you can see here, carbonyl compound, as we said above, is an electron withdrawing group. The formation of this resonance structure is the less stable one because you have positive charge here and an electron withdrawing group. So here is the less stable compound. Also here, again, you see the same structure, and again is going to be the less stable compound. But in meta position, you do not have those resonance structures, and for those reasons, it orients on meta. Okay? So what you have to remember is that those groups orient on meta and those groups orient on ortho and para. But this is just a scheme to let you know that what is the reason behind resonance structures, who has more resonance structures and who who can stabilize more the carbocation, or in the case of this, it destabilizes the carbocation, so making it less reactive towards substitution in ortho position or in para position. So it remains only the meta position. Let's move now to the case that you have a desubstituted aromatic ring and you want to add another substituent. Don't worry, it's not as difficult as it sounds. There are 3 rules to follow. The first one is the case that the 2 substituent groups reinforce each other. Here the situation is straightforward. Let's take a look at this example. As you can see here, hydroxy group orients on ortho and para position. Nitro groups orients on meta position. That is this position here, related to nitro. And for the hydroxy group, ortho position are those positions. So the compound formed is this one. You have the substitution at this position. In ortho position related to hydroxy group and in meta position related to nitro group. The second case is what the directing effect of the 2 groups oppose each other. What are you going to do? In this case, the more powerful activating group has the dominant influence, but a mixture of products is usually formed. Let's take a look at this example. As you can see here, hydroxy group, that is a powerful activator, it orients in ortho and para. Para is basis, so it orients in ortho, in this case only in ortho, but also metal, due to the inductive effect, orients in para and ortho position. But due to the OH, that is a stronger activator compared to metal, substitution of the sulfonic group at ortho position. Okay? The last common scenario is when you want to do substitution between 2 groups that are in meta position. It is not possible for steric reason, because it's too hindered. Instead, you can follow another route by starting with a substrate that is desubstituted in ortho position, like in this example. As you can see here, you cannot straightforward substitute here on this compound that is desubstituted in meta. The products that are going to be formed by this reaction is going to have, you're going to have a bromination here and a bromination here that are related to orientation of metal in ortho and chlorine in para, and here chlorine in ortho and metal in para. In order to do this compound that is not formed, you can follow another route. Take another compound that is ortho substituted. Here you can do a bromination in ortho position related to this compound. So you can do a bromination here and also in para position here. Okay? Okay, this is the first part of this video that is going to be followed by 2 other videos and to complete this chapter with benzene. Thank you so much for watching and look forward to see you in the part 2 of this video. Peace.